Yeah, okay. So today we'll basically do the basics of second quantization, and then we will use the second quantization formulation to do coupled cluster theory from Thursday. And you will see how beneficial second quantization is when we do coupled cluster theory. So second quantization is basically a algebraic formulation which enables us to shift the antisymmetry of determinants to the property of operators. The advantage then is that we can derive expressions uh, for various electronic structure theories without having to write out determinants and evaluate them. Because as you have seen, it is not only cumbersome to write determinants by hand, it is also expensive when you want to evaluate the value of some determinant overlap or some determinantal matrix element. So if you can simplify expressions at the operator level and then take matrix elements only at the very end, which is hopefully a simplified form of the expression, that makes both your formalism as well as your computation easier. So that is the main goal of second quantization. And the main ingredients in the second quantization are the creation and annihilation operators. So the creation operators are denoted by a dagger. So A tells you that this is a second quantized operator. I is the label of the spin orbital. And the dagger tells you that you're adding an electron in that spin orbital. Okay? And you have annihilation operators. Which are denoted by A with the label of the orbital, spin orbital in which you're destroying an electron, and it doesn't have the dagger. Okay, so I'll summarize the action of these operators, which we did last class. So if I have a determinant of with some string of spin orbitals, this is an n electron determinant with n number of spin orbitals, and I am creating an electron in orbital I, which basically means that I add a row and column to my determinant.
Hello, ma'am.
Yeah.
Ma'am, I cannot see your screen. I think it's freeze. Just I am able to see creation operator AI dagger.
Oh, it's
Up to
frozen.
that. Yeah, it's frozen.
Oh, okay. Let me see. Let me stop broadcasting, and then I will start again. Can you see now?
Yes, ma'am.
Okay. So basically you add an electron in spin orbital I. So which means you add a row and column to the determinant, the original determinant. And I write this additional spin orbital here. And now this is an n+1 electron function. Okay. And the important thing is that both creation and annihilation operators, they only act immediately on the like it attacks right next to it. So when it creates in the first place of the determinant, and when it destroys, it can only destroy an electron if it is right next to it. So this is a part of the convention which fits in with the antisymmetry of determinants and keeps all the signs intact. We will see how this works out. So this is the creation operator. And also when you have a string of creation operators, they will also create things in order. So first you will have a chi I and then a chi j. So this is now an n plus 2 electron function. And then we showed that if we reverse the order of creation of of two electrons in orbital I and j, then I interchange the order in which the spin orbitals have been created in the new determinant.
Ma'am, your screen is again frozen, I think.
It's again frozen.
Oh.
Okay. Maybe the internet is not good today in the department. Yesterday, actually, a lot of people had problems with the internet, but I thought today would be okay. So let me see. Stop. But you can hear me properly.
Yes, ma'am.
That is strange. So when I'm scrolling my screen, is it scrolling on your?
Yeah.
Okay, but then it stops suddenly. Okay, let's try again. So I have reversed the order of the creation operators, and I get a determinant uh, which has an. Now what happened? Okay. So yeah, so which has the two operators in reverse order, which means they are related by a negative sign. Okay, so this is equal to minus of chi j
Madam,
chi I. It's frozen again.
yeah, but what is the implication for this creation and annihilation? Because in the physical systems, you must conserve the mass or energy. So where does the other part? If you're creating something, you must annihilate something also.
Yeah, so this will come when you're evaluating expectation values. So the real quantities, the observables, are always expectation values, and you will see whenever you have expectation values, you will need an equal number of creation and annihilation uh, in the string of the operator for it to be a valid physical operator. So what we will do is we will represent things like the Hamiltonian or other physical quantities like the dipole moment as some value multiplied by a string of creation annihilation operators. And this string of creation annihilation operators will be number conserving when they are representing physical operators. Does that answer
Okay,
your
ma'am.
question?
Yes.
Yeah. Yeah. So So let's see. Yeah, so this is related by a sign. So for now, we're only doing the formalism. We're only talking about the wave function. So there you can do anything you want because it's not observable. Okay, so chi j ki, this is related by a sign. So when I add equation 1 and 2, I will get a 0 on the right hand side, and which will tell me that AI dagger AJ dagger plus AJ dagger AI dagger is equal to 0. This is adding 1 plus 2, and this is called a anti-commutator when you have a plus sign. You are all familiar with commutators which have a minus sign, and in this case this is called an anti-commutator. So creation operators anti-commute. Similarly, I guess you can already see it if you have annihilation operators. If if you have AI AJ acting on. So the only thing that's different here is one step. So let's say my chi I and chi j are somewhere in the middle at some arbitrary position. Then before I can make AJ act on the function, I have to interchange the relevant orbital with the first orbital, which will get me a negative sign. So that is the only difference when you're working it out for the sorry, I have a cold. When you're doing this, and then again you so what did I do? Oh, I should have brought chi j over here. So I want to act AJ, so this will be chi j. Okay. Yeah, and then I have to bring again chi I here, which will remove this minus sign now, and I will end up with something something chi k something something chi n with both chi I and chi j gone. And then you can again do AJ AI, and this will give you a opposite sign again when you will do work with the annihilation operators. The reason being that okay, I'll work it out anyway. It's better to work it out then. So AJAI chi k acting on chi I chi j chi n. I'll write another orbital here. Okay, that will help me keep track. Then chi k, and this will be chi n. So there. Now I have to bring chi j. Okay, now let's look at 3 and 4. So you see that chi L and chi K are interchanged in 3 and 4. Therefore, they are related by a negative sign. And then now when I add say 3 and 5, then I get 0, which gives me the anti-commutator of the annihilation operators. So the creation operators anti-commute among themselves, and the annihilation operators anti-commute among themselves. Okay. And from the fact that AI AJ plus AJ AI equal to 0, you see that AI AJ is equal to minus of AJ AI. So if I interchange two annihilation operators in a string of operators, I have to just change the sign of the function. Okay. And this is what we will do repeatedly when we derive expressions. So you can remember this. So you'll use this. You'll learn this up anyway. So every time you have two creation operators and you interchange the position, you get a negative sign. Similarly with two creations. Now what remains is the relation between the creation and the annihilations. So if I have a string, a mixed string of creation and annihilation, if I want to interchange the position of a creation and an annihilation, if I want to switch their places, I need to know the relation between them, whether they commute or anti-commute or whatever, how they are related. Okay. Now, before we do that, I pointed it out last time, but in case you missed, so these anti-commutation relations also incorporate the Pauli exclusion principle. So the Pauli exclusion principle tells you that a spin orbital can have only one electron. You cannot have two electrons in the same spin orbital, which basically means that you cannot destroy two electrons in the same orbital, and you also cannot create two electrons in the same spin orbital. And if you put I equal to j, then you see that the AI anti-commutator equal to 0 tells you that the AI string itself is 0. So whatever function AI acts on, it will return a 0, okay, irrespective of what was in the determinant in the first place. Also, if you have AI dagger anti-commutator equal to 0, it means that so yeah, I guess you understood. So that's 2 and they will cancel the 2. So if you create two electrons in the same spin orbital, the operator itself is 0, which means it does not matter what the function is. For any function, this will give you a 0. Yeah.
I think
Your voice is breaking. I cannot hear you.
He's saying, I think the screen is frozen.
Oh, the screen is frozen again. Okay. I'm so sorry. Maybe it's better when I teach from my home. So let's see. So how much did you all miss? So this is still a recap, so I hope it's okay. So we did the Pauli exclusion principle. And the anti-commutation relation of the creation and annihilations, they encompass both the tenets of the Pauli exclusion principle, which is that you cannot create two electrons in the same spin orbital and you cannot destroy two electrons in the in a particular spin orbital. Okay. Now, the other question that we addressed last time is why do we call AI so let me put it in a better way. So is AI dagger a creation operator when AI is a destruction or annihilation operator. So we want to show that is the adjoint of a creation operator really an annihilation operator. So when I started off today, I just defined AI dagger as a creation and AI as a destruction or annihilation operator. But I did not justify why I can do that. So let's see if defining the adjoint as a creation operator is justified. So I have a determinant K, let's say a 2-electron determinant, chi I chi j. Okay. So I can write this as AI dagger on 1 electron determinant. It doesn't mean anything, but yeah, okay. Then if I take an adjoint of the whole equation, then I have a bra K, which is basically chi j AI dagger dagger, which is chi j AI. Okay. Now what we know is that K overlap is 1. So this is a normalized. Now what happened? And this means that chi j AI K is equal to 1. So from the right hand side, and we also know that chi j is 1. We know this. We know this. Therefore, we can identify AIK with chi j. And remember, K was chi j, which means that the adjoint of AI dagger, which is AI, destroys chi I. So therefore, AI destroys chi I. Okay. This is the justification for calling the creation operator AI dagger when the corresponding annihilation operator is AI. Okay. And you can also verify the commutation relation. So we had the AI dagger AJ dagger plus AJ dagger AI dagger equal to 0. Taking adjoint of the whole equation, we get AJAI plus AIAJ equal to 0. Fine. Remember, AB dagger is equal to B dagger, A dagger. The order is reversed. Okay, so this is what we had done last class very quickly. So today we will continue now. Now this is new. So now we come to something else. So we define something called a vacuum state. Because remember, we don't want to have any determinants in our formulation. So we should be able to write a determinant entirely in terms of creation operators, not as a derivative of some other determinant. So the vacuum state is basically an empty state with nothing in it. So no electrons, a zero electron vacuum state. And the vacuum state is also assumed to be normalized. And any wave function psi can then be written as a string of creation operators on this vacuum state. So this is how you get rid of any determinant whatsoever. So any determinant is written as a string of creation operators on the vacuum state. Then, since you can do that, then if you want to evaluate, let's say, the overlap of two determinants, K and L, you simply write each of them as a string of creation operators and evaluate the expression. So let's do a 2-electron determinant. So let's say K is equal to AI dagger, AJ dagger on a vacuum state, which basically means it is chi I, chi j. And L is let's say a K dagger, AL dagger on the vacuum state. Then this is chi K, chi L. Okay. Now KL overlap is then the vacuum state, and this is an adjoint, so you will have AJ, AI, and AK dagger, AL dagger. Oh, I missed to tell you something. I did not derive the relation between the creation and the annihilation operators, and we will need it right now. So relation between creation and annihilation operators. So to do that, it's quite simple, really. So first we will take AI dagger and AI, so same index quantities. And let's say we will take case 1 when I is empty. Then AI dagger plus AI dagger AI acting on some determinant which does not contain I, remember. If it does not contain I, the action of AI is 0. So you only have the creation in AI and then again destruction in AI, which means that the determinant remains unchanged. Then case 2 is when I is occupied. Then the action of this string, say you have chi I somewhere. So if it is occupied, then the first term is certainly 0. So you can only destroy it. But remember, you have to get I here. So you first generate a negative sign. Then you have AI dagger. And AI has destroyed chi I after bringing it to the first position. And now again, I am creating chi I. But the position of I and k are interchanged with relative to the original determinant. So this sign will again go away. If I want to go back to the original determinant. So there. So from equation now, so the thing is that when I is empty and when I is occupied, the action of AI dagger plus AI dagger AI, it gives you back the same determinant. So which means that for an arbitrary case, when you don't know if I is empty or occupied, you still know the action of AI dagger plus AI dagger AI on a determinant. This always gives you back the same determinant, which means that AI dagger plus AI dagger AI is equal to 1. So this is the relation between a creation and an annihilation operator when they have the same orbital label. Okay, so we have discovered one relation. Then the next situation is for I not equal to j, which means I want to find out what so let's do I not equal to j. Then I have AI AJ dagger plus AI dagger AJ. So what happens here? So the only situation when the first term is not 0 is when j is not occupied and I is occupied. And the situation when the second term is non-zero is when j is occupied and I is not occupied. Now, in a given determinant, you can only have one situation, that is either I is occupied, j is not. You cannot have I both occupied and unoccupied, and you cannot have j both occupied and unoccupied. So you will only have one or the other, which is 0 or non-zero. But so the only situation that we need to figure out is when either j is occupied, I is not, or I is occupied, j is not. So did you get the argument? So the thing is, if sorry, I wrote the that's why I got confused. 1 second. So I want to find out how to interchange these two. So it's basically this. Okay. So I want to find out how to interchange a creation and an annihilation, the same one. So AI, AJ dagger, and the same operators, AJ dagger AI. So that's why it wasn't working out. So here, since J is, you have a dagger on J, then for the action of this operator to be non-zero on a determinant, J must be unoccupied. So J must be unoccupied. And again, for the action of AI to be non-zero, I must be occupied. So that is the only situation we need to look at. So let's do that. So AI AJ dagger plus AJ dagger AI. And we take a determinant, which is again chi k something chi n. Now from the first one, we simply get chi j, chi k, chi n. From the second one, let's say I have chi I here, I will get a negative sign because I need to bring it in front. And then I have AJ dagger, and chi I is gone, and I have chi k in the middle. Here also I had chi I somewhere in the middle. So that one I need to bring up, and then I will destroy it. So AI chi k, created chi j here. And then chi I have brought in front, then I have destroyed it. Okay, this is gone. So here I get chi I, which is a minus, and I have destroyed it. So chi j, chi k. Okay, note that here I have interchanged the position of chi, the chi j with chi I, and here I have interchanged the position of chi I with chi k. So the position of these two, the position of chi k in the two determinants, they are different. So I have one more relative negative sign to take care of. Okay. So although they look sort of similar, I need to get chi k to this position, which involves one more change. And this is a plus then. Okay. And this is 0. So, okay, so because I didn't write too many orbitals, it became a little bit confusing. But if you write, say, another chi L or something, you will notice that it becomes clear. So in the first determinant, when I come here, the position of chi k is right next to chi j. However, in this one, chi k is at the original position of chi I. So they are not in the same position. So if I want to take chi k to the original position of chi I, it will involve one more change, which gives me another negative sign. Okay, and this gives me a 0. So what did I get? I saw that when I was equal to j, the action of AI dagger plus AI dagger AI is 1. And when I is not equal to j, then the action is 0 in all cases. So whether I and j are both occupied, or I and j are both unoccupied, or when I is occupied, j is not, or when j is occupied, I is not. So in all cases, the action is 0 because of various reasons. Therefore, I can combine the relations for all the situations and write it as delta ij. So when I is equal to j, the anti-commutator has a value of 1, and when I is not equal to j, the action of the anti-commutator is 0. Okay, for all possible determinants. So this means that I can write AI AJ dagger as the delta IJ. Hello? Hello? Can you hear me?
Yes.
My internet got disconnected. I think the internet is really poor today.
Yes. Yes, it is. for IISER Wi-Fi.
Yeah. Okay, so I don't know where it got disconnected. Anyway, so let's see. So we found the relation between the creation, the annihilation, and the creation annihilation. So now when we want to evaluate the overlap, we want to evaluate the value of this string that we saw before. So the strategy always is to uh, get as many terms zero as possible. So, so you look at the determinant on one side. Usually you look at the ket on the right because that's easier to think about, and you try to destroy it. In this case, since it's a vacuum, if I can move AI to the end or AJ to the end, I will destroy the vacuum and I will reduce terms. So my strategy will be to move this AI to the right. Okay. Alternatively, if this determinant was something else, like for example, a Hartree-Fock determinant with occupied orbitals, and let's say L is an occupied orbital, then I would try to move the creation operators to the right if they were not already on the right. So the goal is to annihilate the ket in almost all the manipulations that we will do. So here, if I want to move AI to the right, I have to first switch it with K and then I can switch it with L. So AI AK dagger, we can use this relation to write it as delta IK minus AK dagger AI AL dagger. Right. Okay. And then we will again so I have AJAL dagger as the first term with the delta IK, and I have a second term which is AJAK dagger AIAL dagger. Now here it's again the vacuum, so you can only so L must be equal to J because you will create only chi L, and then J must be L for it to exist. So you will have a delta JL over here. And here I will move again AI to the right, which means I will get a delta IL minus AL dagger AI. Now this, you're destroying I when I is not there. So this is simply 0. And I Oh, hello. Okay. Okay, let me just then finish one more line since it did connect. I'll just finish this and then we will let it be. Today is not a good day. Okay, so basically you have a delta JK here and a delta IL. So now you have got a nice easy expression for the overlap of K and L. Okay. So that's it. So if you know
No, are you presenting?
I, J, K and L. Yeah. You can see?
I can't.
Okay. Let's leave it here for today. The
Uh,
internet is creating a
the,
lot of problems.
the first term vanishes. Delta JL, delta IK.
No, it's there.
Okay. But, okay.
So and this is again only J can only be equal to K. That's all because you are create in a vacuum. You're only creating K, so you can only destroy that one. You cannot destroy something else. So you get a expression in terms of delta functions. Okay. So I had wanted to do some more and finish second quantization, but since we did not manage, I will complete it on Thursday and then start on couple cluster theory. Okay. Let's stop for today. Thank you.